Hello again. This is another video for chapter 3, and I'm going to start with the section I believe was 3.4. So let me get started here. Yes, 3.4. So what we want to talk about in this video is these probably 2 or 3 sections. See how much time we have. First one is about derivatives as rates of change. So I hope you're doing well. So let us get started. So I want to talk about the fact that we know the definition of instantaneous rate of change at a given point A. We know is that limit right here, right? And the way we get it is we let h approach 0. What if we assume that h is close to 0 but is not as close as we want it to be, so we can get the limit? We just say x is close to 0. Let's say within 0.1, 0.2, right? Really close to 0. So if that's the case, then we can say that the left side is actually approximately equal to the right side. And if that's the case, then we can cross multiply, right? And isolate f of a plus h. So it would be h times f prime at a plus f of a. So that means if I have a function and I want to find, if I know the value of function at a, so if I know f of a, and I know the value of the slope of the tangent at a, right? So if I know the slope of the tangent at a, and I'm making a mess here, so let me fix it. So if this is a, and I know the value of a, f of a, and I know the value of the tangent at a, the value of the slope of the tangent, which is f prime, then I can find the function value at a plus some number. Let's small positive number or small negative number to the right or to the left of a. So the value of the function at this point is going to be, of course, that right there, right? So it would be about this distance. But instead, I can use this distance, right? So from here to here, which is the distance from the x-axis to the intersection to the tangent line. And you see a better picture of it here. So I'm going to use this right here, right? So here's a. I know the function value at a, and I know the slope of the tangent to the graph of the function at a. So what I want to do is to use those two values, f at a and f prime at a, and the fact that I have just a small distance from a to the right or to the left of it, I want to find the function value at a plus function value at a plus h, at that value right here. So what I want is actually this, but instead I can use this. That's what that is. So so we can use this idea to approximate function values, right? So let's do an example. So I know that 1 to the x to the third power, so you know the function x to the third kind of looks like this, right? So here is 1. I know the value at 1 is 1, right? So I know f at 1 is 1. And I know f prime is what? What's f prime of x to the third? Well, it's 3x squared, right? So what is f prime at 1? What would be 3, right? So I know f prime at 1 is 3. So let's say I want to find the value of 1.01 to the third power, right? What is that? Well, to do that, what I want to do, I'm going to use that formula that says that f of a plus h equals to f of a plus f prime at a times the change, right, from a. The change, the amount of change is just 0.01, right? So that's it. That's the difference between a, right, and a plus h, which is h. So that's the idea. So I'm gonna use that. So I'm gonna say f of 1.01. So f of 1 plus 0.01 is f of 1 plus f prime of 1 times 0.01. And that's my estimate of what 1.01 to the third power is, right? So this is useful, right? Let's say this was x to the 100th power. I still add 1 would be 1, and I can find the prime and find that. But think about it, if you take 1.01 and raise it to 100, that takes a long time. But you can approximate it this way, right? So if you use a calculator uses 14 decimal places. Here we only have 2 decimal places, right? So, but it is close, right? That's the answer we got, and here's the answer the calculator has. So that's one way to use the idea of derivative to approximate function values, right? And later we're going to talk more about this as a linear approximation, but for now, that's what this is. All right, so let's apply it to an example of motion along a line. We talked about position function. So if we have the position function, the derivative of it is velocity. And if you take another derivative, that means derivative of velocity is acceleration. So acceleration is really double derivative of the position function, right? So if we go from position to velocity, we take one derivative, take another derivative, we get acceleration. Now in chapter 5, we're going to learn how to go back. And if we are given acceleration, how do we find velocity? And if we are given velocity, how do you find position? And that is called integration. This is called differentiation, and this is called integration. They're two kind of parts of calculus. Historically, interestingly, calculus started with integration, but most textbook, almost all of them, there are a few that start with integration and then they get to differentiation. But most textbooks nowadays in the world, they start with differentiation and then they get to integration. All right, so let us apply this. So here is a position function of a particle moving on a horizontal line, right? Find the velocity and acceleration functions. Determine the time intervals when the object is slowing down or speeding up. Now, when the velocity is positive, let's say we define it going to the right to be positive, right? Now, if you measure on the let's say on your axis, start from 0 and positive numbers are on this side. So if you start increasing your distance from the initial point, then obviously your velocity, your position is increasing, so change in position is positive, and change in time is positive. So obviously your velocity will be positive, right? So we're going to say to this, going to the right, velocity is positive, going to the left, velocity is negative, right? So if we're going to the left, velocity is negative. Okay, what about acceleration? Well, acceleration is the rate of velocity. So if the acceleration has the same sign as velocity, so if the acceleration is positive and velocity is positive, then the object is speeding up to the right. If the acceleration is negative and the velocity is negative, then the object is accelerating to the left. Otherwise, if the signs of velocity and acceleration are different, then the object is slowing down. Okay? So let's say velocity is negative, right? And acceleration is positive. It's like with your car, you're going in this direction, right, to the left. So your velocity is negative, so your position is increasing in the other side, in the negative side. And then you apply the brakes. They apply the brakes will be in the other side, in the other direction when you apply them. Is against the rotation, the direction of rotation of the wheels. So if the wheels go this way and you go left, then the acceleration is this way. So acceleration wants to move you backwards. So acceleration has a negative sign, right? So in this case, we say that the object is slowing down, going left. If the velocity is positive and then acceleration is negative, right? In this case, your wheels are going this way and taking you to the right. But then when you apply the brakes apply an acceleration in this direction. So that means the brakes again want to move you backwards. So what happens is that we say that the object is slowing down, going to the right, right? So that's the idea. So it means that in order for us to find out when this object is slowing down or speeding up, we need to sign analyze or do sign analysis for velocity and acceleration. So first of all, let's find them. So here is velocity and here's the acceleration. You have to take derivatives, right? And here are the graphs. But without the graphs, let's see what we can do with these. So we're going to set this equal to 0. How do we do sign analysis for a function? Well, sign analysis means in 2D, it means that you want to find out when, at what point the function is 0. Then we're going to find out at what points the function is not 0. That means either positive or negative, right? So 0 for a function means crossing the x-axis, right? So here the acceleration is in red, and you see is 0 here, and it's going to be 0 again over here somewhere, but that's a negative value for t, and we assume this is t, so we don't really care about the negative value. Okay, and the acceleration is 0 at 1/2, right? And you see it right there. So from the graph, you can tell when the velocity is positive and when the acceleration is positive, right? So for example, over here, right, before 0.5, acceleration in blue is negative, is below the x-axis. And the velocity in red is negative. So that means over here, obviously, the function is what? Slowing down. All the way to what? All the way to 0.5 right here. Why? Because the velocity and acceleration both are negative. But over here, after 0.5, notice the acceleration is positive and the velocity is negative. So here the object is slowing down, right? All over here is slowing down, all the way to this point right here. And from this point on, both velocity and acceleration are positive, so the object is speeding up. Up to what? Up to this point. And after this point, what's going on? Well, again, velocity is positive, acceleration is positive, it keeps what? Speeding up. So let's look at the table here. So the way we do it, we're going to find out when velocity is 0. So we just set it equal to 0. We're going to do the factoring and find the zeros. And do the same thing for acceleration, find the zeros. So we got -1 and 2. -1 doesn't work for us because time cannot be negative in our example, right? And so we have 2 and we have 0.5, 2 points. Now, the domain of this function is from 0 to infinity. So we're going to make a table here. And we're going to learn more about doing this later. But for now, let's apply this table to this problem. So the first row is the values of t, go from 0 to infinity. And the important values for us here is 0.5 and 2, right? So we'll put them here. And then put vertical kind of segments here. And then create 3 more rows. Velocity, acceleration, and the function position itself, right? So we know that at 2, right, at 2 velocity is 0. So we're going to put a 0 right here where the velocity intersects 2, that's a 0. And then we know at 0.5 acceleration is 0, so we put a 0 here for acceleration. Okay, now we're going to do sign analysis for velocity. Now we are not close to -1, so we're going to go around 2, right? So below 2, we pick a number, let's say 1, and we substitute 1 for t in velocity function. If we put a 1 here, I put a 1 here, we are just interested in knowing whether we get a negative number or a positive number. So if we put a 1 here, that's a negative, and that's a positive, so that would be negative. So basically over here, the velocity is negative, right? And what about after 2? Let's say pick a 3 and put it here. 3 minus 2, positive. 3 plus 1, positive. 6, positive. So this is positive. So velocity is positive here, is negative here. And acceleration is 0 at 0.5, right? If we pick a number below 0.5, let's say 0.3, and substitute it in here. If I put a 0.3 here, 0.3, 12 times 0.3 minus 6. 0.3 of times 12 is smaller than 6, so that would be a negative value. And if I put anything after 0.5, let's say 1, right? then the acceleration will be positive. Okay? Now, at 0.5, you can use a calculator and figure out what the position is at 0.5, right? If you put 0.5 for t here, you get 1.5. If you put 2 for t, you get -12. So at 0, if you put a 0 for t here, is 8. So we know this object started at 8 units to the right of 0 on the horizontal axis. So I have the picture here. So here is 0. Right? I mean, not here. 0 is here. Okay? So what happened is that's a position 0, right? I'm talking about t equal to 0. Right? This is the position. Don't confuse it with the t-axis, right? So that's actually the y-axis. I made it horizontal. When you graph, the horizontal is actually t values and the y is actually vertical. So what I did here, I say, okay, I'm going to put this over here and look at where the object is at any given point, right? So at t equal to 0, the object is 8. The object is 8 units from the 0, right? And what does the object do at 0? Well, the velocity of it would be negative, so it's gonna go what? It's gonna go to the left. So it's gonna go to the left, right? And it's gonna continue going to the left, right? Until what? Until it reaches what? 1.5, right? So at t equal to 0 is at 8, and then at then it's going to reach what? At t equal to 0.5, it's going to reach 1.5, right? And then it continues, right? So that's that point right there, right? and it's continuing, so that's 1.5. You see that's 1.5 right there? That's on the position is 1.5. That means y or s equals to 0.5. Here s equals to 8 and t equals to 0. Here s equals to 0.5 and t equals to s equals to 1.5 and t equals to 0.5, right? And then what does it do? Well, the velocity is still negative, and it keeps what? Keeps going. And keeps going and going and going until it gets to what? Time equals to 2. So it's going to reach way over here, right? At this point. So when t equals to 2, right? And s equals to what? So let me put it down. So t equals to 2 and s equals to negative 12, right? So it's going to be on the other side of 0 now because it keeps going left. Okay, what does it do at this point, right? At this point, the velocity changes direction. It's positive now. Now at this point, it's going to go the other way. And it keeps going. We don't know how long because we don't have any more data. We're just going that way. That's why I put this black arrow here that is going that way. Okay? We don't have any data for that. Okay, so when is it that this object is speeding up or slowing down? Well, look, here is the speeding up because the velocity and acceleration are in the same direction. Here is the speeding up to the left. What is it doing here? Here is the speeding up, is a slowing down to the left. Here is the speeding up to the left because they have the same sign. Here is a slowing down to the left because they have different signs, right? Acceleration and velocity. And here it does the same thing, slowing down to the left. What about here? But here it changes direction and is speeding up to the right, right? And we don't know what happens after that. We don't have data. All right, so you see it's pretty useful to use calculus to understand what is going on and what this object is actually doing. All right, so here is another graph just to practice. We are given the graph of the position, and the position is doing this. The position is increasing here and is decreasing. Position is staying the same and then decreasing and then increasing, right? What's going on with velocity and acceleration, right? And to do that, we just look at what? Look at the graph. Now later we're going to learn much more tools to deal with this, but just to introduce you to what calculus can do for us and the difficulty involved if you don't have calculus, let's look at this problem. So what we want to do, we want to use the graph of the position to determine the time intervals when the velocity is positive, negative, or 0. And then use the graph of the velocity. So we kind of sketch the graph of velocity. We don't know exactly how to graph it, but we can have a sketch of a velocity graph. And then it says determine the time intervals when the object is speeding up or slowing down. So let's look at this. First of all, we can look at if you draw tangent to the position function, the slope of that tangent line is velocity. So it looks like the velocity is positive all the way to this point, which is about 1.5, right? So from 0 to 1.5, right, velocity is positive, obviously. Now, at 1.5, the velocity is actually 0, right? Because the tangent is horizontal. And then after 1.5, looks like if you draw a tangent, see the slope of this line is negative. So the velocity is negative here. Then the velocity is what? Is again 0 over here, right? The velocity is 0 here, positive here, negative here, 0 here, negative again here, and 0 again here, and then positive again here, right? So those are the signs of velocity. And you can put the intervals, don't include the points, just, from 0 to 1.5, and from 6 to 7, from 6, you see, to 7, we don't have more data, is positive. And from 1.5 to 2, from 1.5 to 2, just in this little part right here, the velocity is negative. And from 5 to 6, from 5 to 6, about this part right here, the velocity is negative. And it's 0 on 2 and it's 0 at 2 to what? To 5, right? Of course, those are intervals. We also have what? At these points, velocity also is 0, right? But we are asked to find the intervals, right? So in this interval, why is velocity 0? Is because the slope of the tangent is 0 and position remains the same. Notice that position doesn't increase or decrease, right? Okay, so based on that, we can kind of have a sketch of the velocity. So we can graph it from 0 to 1.5 is some kind of positive value. At 1.5 is 0, right? We see it here. And then from 1.5 to 2 is negative. Then again at 2 is 0. And then, at 2 it jumps to 0, right? It jumps over here. And then what? Well, from 2 to 5, it stays 0, right? Up to here, right? Stays 0. And then after 5, it jumps to some negative answer, right? And then we don't know exactly what negative, well, we just, guesstimate it. So it's a negative value all the way to what? To 6, where again is 0. And after 6 is positive, all the way to 7. And we don't know what's going on after that. Okay? Now, what about the speeding up and all that? Well, acceleration is positive on 5 to 7. 5 to 7. How do we know the acceleration is positive from 5 to 7? Well, think of it this way. If I draw tangent lines to this, notice that tangent lines have big negative values and then they approach 0. So we start from some negative value, right? So we start from some negative value. I lost my pen here. So we start from some negative value and then we go to 0. If you go from negative to 0, that means that value is increasing, right? See, on the number line, if you go from negative to 0, you're actually increasing. So that means the slope of the tangent line, the slopes of the tangent lines are increasing. And remember, f prime is a function itself. So if the values of f prime are increasing, that means the prime of this, the prime of the velocity, in this case is of course s, I just put s. So the prime of velocity, which is double prime, has to be positive. Why? Because they are increasing. So over here, from 5 to 7, the acceleration is positive, right? And then from 0 to 2, right? From 5 to 7. Now, what about over here? Over here, the values go from 0 to some positive values, right? So from 0 to positive, so acceleration is going to be positive again. Why? Because the slopes are increasing. So slopes are increasing here, the slopes are increasing here. Don't look at the black graph. The black graph is decreasing and increasing. We're not talking about that. We're talking about the slopes of the tangents to the graph, right? Those are increasing on both sides. So that means from 5 to 7, acceleration is positive. And from 0 to 2, think of 0 to 2. Let me erase my stuff. So from 0 to 2 here, from 0 to 2, right? So up to here, you see the acceleration is basically the rate of these slopes of the tangent lines, which they start with some positive number, right? And then go to 0. So that means is what? The slopes are decreasing, right? And here they start from 0 and they go to some negative value. So they go from 0 to negative, that means they're decreasing. Here they go from positive to 0, that means they're decreasing, right? So that means in this area here, in this interval, acceleration is negative, right? From 0 to 2. And acceleration is 0 on 2 to 5. From 2 to 5 is 0 because the velocity is 0, right? If the velocity is 0, acceleration is 0, right? All right, so when is it that the function is increasing, speeding up or slowing down? Well, the object is speeding up on 6 to 7 and 1.5 to 2. Why? Well, because the acceleration and velocity have the same sign. And it's slowing down on 0 to 1.5 and 5 to 6 because the acceleration and velocity have different signs here. That's why. Again, that's we're going to learn more tools to deal with situations like this. But for now, that's just an introduction to what calculus can do for us. All right, so let's apply calculus to some other applications. Here is a website that in the notes again, if you click on it, you go to this website. It's called breathing-earth.net, and it's supposed to show up right now. Here you go. So what it does basically, if you go over any country, at the bottom right here, you see the rate of increase of the population. So right now, the population of the United States is 326,668,044 people. And unfortunately, I'm not sure if this is including all the coronavirus deaths that we have had, up to almost 100,000 people unfortunately died. So now what it does, it shows the rate of people dying and the rate of people right now being born, right? So right now, the rate of people dying is one person dies every 12.1 seconds. And then one person is born every 7.4 seconds in the United States. And as you look at it, you see the population actually changes. You see right now it changed to 47. It was 46. So that's a real time, basically, animation based on data. And how can they do that? Well, using calculus and linear algebra and differential equations. That's how this is done. So you go over any country and you can see also other data. Right on the right hand side, you see in the middle, you see currently how much CO2 we are emitting. And then on the right, you also see number of people that have been born in the world and number of people that have died in the world. Right there. I'm not sure if this includes the coronavirus deaths recently or this is older data. I'm not sure about that. But for now, that's population of the world right now is about 7.6 billion people. So it's an interesting website. You can go over any country and find out the data about them. All right, so let me get out of here and go back. So what we want to do now, talk about application of calculus to population change. Just like we can think of position function and take the derivative and think of velocity, we can also take a function like population growth and take derivative of it. That gives us the rate of population growing, obviously. So here is an example. It says, in a small town in Ohio, commissioned an actuarial firm to conduct a study that modeled the rate of change of the town's population. The study found that the town's population, measured in thousands of people, can be modeled by the function that, P of t, where t is measured in years. Find the rate of change P prime. So P prime would be rate of the population growth in that town, right? And interpret P prime of 1, P prime of 2, P prime of 3, and so forth. Interpret P double prime of 1, P double prime of 2, and so forth. So let's do that. So first we take the P prime. Obviously P prime would be this function right here, right? 3 comes downstairs, becomes a -1 times t squared plus 64. Now, here are the values of P prime 1, P prime 2, P prime 3, and so forth. So over the 4 years, you see the first year, the population was changing about 63,000, right, per year, increasing. The second year was 60,000, right, increasing per year. The third year, 55, and a year after that, 48, right? So that's what that is. Now, what about P double prime? Well, P double prime would be the rate of rate, right? You can think of the acceleration of the population increasing. How fast the rate itself is actually changing. And so the derivative of this would be -2t. Derivative of that is 0, so that's it. So P double prime of 1, 2, and 3, and 4. What does that say? Well, that means the rate at which the town's population is increasing is decreasing more and more. For example, the first year was -2, right? The second year, -4, and so forth. So the rate of the population change is actually decreasing, right? You see that? Now the rate is still positive in 4 years. That means the population is increasing, but is increasing with a slowing what? Slowing rate. Now this idea will be, we're going to talk about this much more. And the idea is this: when something increases at first, is increasing like exponentially like that. And then there is a point right here where the population is still increasing, but with decreasing rate. And notice the slope of the tangent line here. What is going on with the slopes of the tangent lines? Well, first is like about 0, maybe close to 0, and then it becomes what? Sharper and sharper up to this point, right? So the rate itself is increasing up to this point. But after this point, what happens? We start with this slope, and then we go to what? We go to those slopes. Those are smaller values. So that means the rate is decreasing, okay? So if you relate that to the spread of coronavirus, at first it was exponential, and there was a point in the middle where the spread starts what? Flattening. That's what flattening means. So basically what we want to do, we want to reach that point as quickly as possible. So we don't want to wait for the function to go and reach it naturally. If we do that, then hundreds of thousands, even millions of people can die before it slows down. So by social distancing, which unfortunately we did it late in the United States, we were about 2 months late. So there is a price that we paid, and that a lot of people are dying because we did that late. So this thing increased too much before we cut off. Well, we still don't know at this time. I'm not sure we have done it or not, but in some states it looks like we have reached that point and passed it. In some other states maybe we are over here, we don't know. Maybe a few more weeks. Right now it's like what is today? It's May, so if you look at this later on, it's May 25th. See what happens. Hopefully in Texas we're not going to have that much increase, but right now we don't know. All right, so let's move on. Now let's apply it to economics. So in business, they have cost function, they have revenue function, they have profit function, and they have price function. They have more functions, but those are the ones that we're going to work with. So cost function, of course, gives you the cost of producing this many items. Revenue function is the revenue that you make by selling this many items. And the profit is profit you make of selling this many items, right? So when we take derivative of these, well, derivative obviously is going to be the rate of change of cost, rate of change of revenue, rate of change of profit. And in business, they call them marginals. So marginal profit, marginal cost, marginal revenue, right? And we know that the profit function is revenue minus cost. And when you take derivative of it, well, derivative of profit would be revenue, derivative of revenue minus derivative of cost, right? Because it's the difference of two functions. When you take derivative, it would be the difference of two derivatives, right? Now, something interesting happens in business, and that is, well, we know these are the definitions of derivatives, right? But remember, x here is actually an integer, right? Is a positive integer. So when we want to approach some number, we cannot go in the middle, right, of these numbers, because number of products can only change from like 2 to 1 and then to 0, right? So if we are at some level, let's say we are producing 200, and we want to take the derivative, well, we're not going to be able to approach 200, like get really close to it. The closest number to 200 is 201, right? If we go to the left of it, it would be 199. But that's 1 unit. So h, the smallest h can be is what? Is 1, right? So if that's the case, then why don't we say that when h is 1, we can say that this equals to this, approximately, right? So when h is 1, we're going to say that this side is equal to this side approximately. So h is 1, it goes away in the denominator, and this becomes 1, right? So the rate as at x number of units of products is going to be approximately, the rate of change would be the difference between cost of producing x item and the cost of producing one more item, right? So that's the idea. What's the rate of revenue that you're making when you're selling X units? The rate of revenue is approximately the difference between selling X item plus one item and X item, right? So that's the idea of derivative. So in business, instead of calculating this limit, what do? You could just do it approximately. How much profit do you make of selling, let's say, 100 units plus 1? And how much do you make at 100? The difference is the rate when you're selling X number of products. That would be the rate of profit when you're selling 100 items, right? So it's a kind of an easy formula to calculate the rate in business. So I just described this. You can stop the video and read it. I just talked about it. So let's look at an example. Suppose the price, demand, and cost functions for the production of cordless drills is given by this. So don't confuse this with profit function. That's price function. That means the price depends on number of items, right? So in business, the price is not fixed, right? When a new product comes in the market, the price gets fixed in the market, right? Depends on competition, depends on how much it's going to cost you to produce this stuff. So all of that, I give a function. So price itself has a function. That's a lowercase p. Profit is upper, a capital P, right? So how do we calculate the revenue? Well, revenue would be price times how many you sell, right? So if you take the price function and multiply it by number of items, you get revenue, right? All right, so let's do that. So we got the cost function. We don't have revenue function, but we can find it. And then we don't have profit function, we can find it, because profit function is revenue minus cost. Okay, so let's do that. So we're going to answer all of these questions. Find C prime, find R of X and R prime, and all of that, and interpret them. So let's do that. So first of all, C prime, or here's C. What's the derivative of C? Well, derivative of 75,000 is 0, and derivative of 65x is 65. So that's it. Right? So that means rate of cost, right, at any x value is basically fixed. It's 65. Right? Now, what about revenue? Revenue would be price times, this is the price function, times x. So that's the revenue. So revenue equals to this. So what's the rate of it? We take the derivative, 143 minus 2 times this, x to first power. And what's revenue? What's the rate of revenue at 1,000 products sold? Well, we just put 1,000 in here, right? And the answer would be 83, right? Just put 1,000 for x. What is revenue at, what is the R prime at 4,000? Negative 97. What does that mean? Well, that means when you're selling 1,000 product, your rate of revenue, making revenue, is actually $83 per product. When you're selling at 4,000 items, your rate actually is negative. That means you're actually losing revenue per item, $97 per item. Why is that? Well, it depends on the cost function, depends on the price function, right? They're all related. So what they do in business, they try to maximize profit. So maximizing profit doesn't always mean that you sell more. That makes sense? You see that? All right, so D, profit. What is profit? Well, profit is revenue minus cost. So revenue minus cost function gives you a function for a profit, and take the prime of it. So that's the rate of making profit, right? Now, how much, what is P prime at 1,000? $18. What's P prime at 4,000? Negative 162. What does that mean again? It means when you're selling 1,000 items, your profit is about $18 per item. When you're selling at this level, you're losing $162 per item, right? And that's the idea, $162 per item. All right, of profit. All right, so I'm gonna stop here, make this video just be about rates, and next video I'm going to talk about derivative of trigonometric functions. Okay, we'll make the videos a little bit shorter. This way you can take a break and come back and watch another video. Okay, so I'm going to say bye to you and see you in the next video. Take care of yourself and others.